Hello, welcome to the third lecture of this series. So today we look at the complex plane. Which we denote C. So we look at the properties, the structure of the complex plane. So what kind of structure? Firstly, whether there exists distance, metric structure, topological structure, algebraic structure. Alright? So let's look at the set. Set is of this form, where A, B are real numbers. Alright? Now, once you write this, C, there is a map from C to R2, which is very clear that A plus IB goes to A comma B. Alright? Now, whatever we have studied, the topological properties or the metric properties, what we studied in R2 can be pulled back here in C. For example, we want to find a distance in C. So distance so the way to visualize complex numbers is R2. Alright, so that is very important. That is very important. So this is x-axis and this is y-axis, and A plus IB, A goes in this direction and B goes in this direction. So this is A plus IB. We will denote this as A plus IB or A comma B, depending on whether you are looking at the complex plane C or R2. Alright? So the distance from 0 would be the distance in R2. So the distance in R2 will be considering the distance in C. So the distance between 2 point distance between, let's say, A plus IB and 0 is defined to be distance of A comma B 0, which is square root of A square plus B square. Similarly, distance between 2 points A plus IB and C plus ID is defined to be distance between AB and the usual distance here, AB and CD, which we now know. We know from coordinate geometry this is A minus C square plus B minus D square. Alright, so this is the distance. The distance between two complex numbers is defined that this way. Alright, the distance between the points which are actually identified in the art. Alright, now once you have distance, you have the notion of open sets. Alright, so of course the basic open sets we should write sets of the form D A. Well, here I would write, let's say Z comma R, which is Z, which is x plus IY, and C such that x square. Here let's put here a plus ib. So z in C such that x minus a square plus y minus b square less than r square. So this is called d a plus ib, comma r is called the disk centered at a plus ib and with radius r. Alright. Now what we want to do is define the open sets. Oh, so one more thing here. So the distance between 0 and a plus ib has a name. It's called modulus a plus ib, which is modulus of a plus ib. We'll come to more about this thing. So this distance, as in R2, satisfies all the property of a metric. The distance defined in C defined as this as 1 satisfies all the properties to be a metric. So it's C becomes a metric space with respect to this distance, which is a standard distance in R2, and well, then we define no open sets. A subset U of C is said to be open if for every point P in U there exists small r greater than 0 such that D, so this is R depending on P, so Rp, P comma Rp lies in Q. Right, and you see these are open sets, you know these things are open sets. So what are this in the picture? Yeah, I should draw a picture here. Alright, so let me erase this distance. And draw a picture here. This is a point A plus IB, and put some R and draw a circle with center at A plus IB and radius R. This is D A plus IB R. Similarly at 0 at the origin, let's say this is R, so this is 0 R. Yeah, fix the notation first. I'll use colon, not comma, so colon here, colon. Okay, so these are the basic open sets. So this inside of circle. So these are basic open sets. Sets, and these will be important for us. Yes. All right. And similarly, the definition of limit points, closed sets are done accordingly. So, limit point P in C is said to be. This is just to recall, it's nothing new, just a repetition. So it could be a limit point E if for every epsilon greater than 0 is E minus P. Well, E intersection D P epsilon minus the point P is non-empty. Alright. Closure as we defined, E union all the limit points of E is said to be closed if E closure is E. Alright? So closure of these disks, for example, this example, mod Z is equal to R is a closed set. And of course this mod Z less than R is open. This will play one of the fundamental role here in this course. So keep on repeating these things. So even this mod Z, of course this means Z in C such that, like this, Z in C such that mod Z equal to R. This is also closed. Similarly, if you want to translate this, Z in C such that mod of Z minus A equal to R is also closed. Alright, so these are a few examples of closed sets which will play important role in this course. Right, this is circle. Circle with center at A, radius R. Alright, compactness. The subset K in C is said to be compact if every open cover of K has finite subcover What is open cover? Open cover, okay, is a collection of open sets. A collection of open sets whose union covers K. Sets whose union covers, well, collection of open sets, I should put in a better words, U alpha. Alpha is in some index set such that K is subset of union of U alpha. Well, so and you know by Hindenburg theorem all the compact sets. So theorem, Hindenburg, a subset K of C is compact if and only if K is closed and bounded. Alright, so a compact subset, a subset K in C is compact if and only if K is closed and bounded. Alright, so we'll come more topological properties after some time, but let us begin with some other properties. For example, the algebraic properties, the algebraic structure. That is definitely crucial one, because topology is just as in R2, nothing new. So what is new is the algebra. Algebraic structure. In C, there are several. Firstly, C is a vector space over R and over C. Right, so when you look at C over R, C over R, and R2 over R, the map which I wrote, A plus IB goes to A comma B. This is a real or linear invertible map. Alright? Of course, this also, you see, this is also an isometry as we define the metric. Alright, so this is one structure, but of course when you consider C as a vector space over C, that changes its role. We cannot say R2 as a vector space over C, so there is something new here, which one should compare with R2 over R or C over R. Alright, so now next one, which is also very important. The field structure. Let's see. Right, so it has field. So which is R2 is not a field. So R2 has no field structure, but C has. That is a very, very crucial distinction. So you have multiplication between two complex numbers which is AC minus VD. So considering I square to be minus 1 plus I BC plus AG. And so you have the inverse on A plus IB is not equal to 0, and you want to look at A plus IB inverse. What will you get? A minus IB by A square plus B square. So this is A by A square plus B square minus IB by A square plus B square. Since this non-zero, that means A square plus B square is not equal to 0. So this makes sense. So this is also a non-zero number in C, non-zero complex number. So it has a field structure. So every non-zero number has an inverse. Field structure is there. And now this field structure enables Cauchy towards his definition of differentiability, just the analogous to R you can make because of the field structure. Let's look at that again. We'll look at more structure in the next video, but before that, let us see an application of this field structure. An application. If from omega to C, omega is a domain in C, and you want to write this, the A belongs to omega, and you want to write f of A plus H minus Fa by H, right? How can you write? Because of the field structure. So this 1 by H, which is H inverse, does make sense. So limit H tends to 0. H is in C, but of course H is non-zero. If H is 0, then this does not make sense. So H is non-zero here. And so yeah, C minus 0 you can put. So this limit, the very crucial point of this limit comes from the field structure, which was not in R2. So you cannot do this. You cannot define this in R2. Right? See the importance. So now this field structure make in such a way that this also would actually gives a lot of things which Cauchy was developing in the process of developing the integration and so on. Okay, we'll see more of algebraic structure in the next video. Thank you.